Okay. So I think you guys had like FE class before this, right? So in this class, we would be mostly discussing some ideas related to functional equations which require like which are mostly based on number theory and which are like which require some divisibility and stuff. And so we will be mostly looking into those kind of FEs. So firstly, if you people have done some NT-related FEs before, what ideas have you seen? Like in problems, you could just tell me.
The main idea for the functional equation, natural numbers to natural numbers, is mainly induction.
Okay, yeah, that's a very important idea. And also, when we talk about NTFEs, it's not just, it won't have to be just from naturals to naturals. It could be from Z to Z as well, from Z greater than equal to 0 to Z, any, all sorts of things. But it's mostly like integer related FEs. So,
Yeah, integer to integer, I
yeah.
say.
But yeah, induction is okay. Induction is quite important. Then obviously you have stuff. Okay, you guys do know Bezout's lemma and all, right? I think you had a class on that. So even
Repeat.
what?
Can you please repeat?
Oh, Bezout's lemma, like if A divides D divides some A and D divides B, then D divides AX plus BY.
Linear combination. Okay.
Yeah, yeah, yeah. Okay, so some divisibility related facts, like some basic number theory facts, and yeah. Then there is this idea of bounding. Like if suppose something X divides Y, then you have that mod of X is less than equal to mod of Y. And the general idea here is that if you can suppose by some argument make X very large, suppose, so that enforces that Y must be zero if you can make X larger than Y. So this is like a very important idea as well. Then you have stuff like suppose you have something dividing a prime power. Also in NTFEs, generally primes are very good numbers to work with, because if you have something dividing a prime power, you already have reduced it to, like, you already know, like it's like it can take only a very few values, like it would only take values which are powers of that prime. So this is also very important. So these are like a few ideas which would I would be mostly using today, and these are generally used a lot in FEs. And also in general, surjectivity, injectivity, all of that, this is like a general idea for all FEs. Like whenever you try an FE, you should always think about these things first, like is the function injective, is it surjective and all. So that is also one thing. Yes. So mostly these are a few ideas, and we'll keep adding on ideas as we do some problems. So let's start off with a problem. Yes, let's start off with it. Okay. Any ideas you people have, you can speak those. Like,
Possible solutions could be f of
yeah,
x is equal to x and minus x.
it's from z greater than zero, so it's
Oh,
just
okay.
f of x equal to x. Yeah, okay. So this is a possible solution. Yes. In fact, this also helps a lot of times. Like you figure out what could be a solution, and then you try to work towards it. So this is a possible solution. Yes.
Also, Fn must be smaller than equal to n.
Uh,
Plugging
how,
m 0.
okay, how do you get that?
M, if we plug m is equals to 0, then Fn divides n.
Oh, it's greater than zero, right? So you can't really put zero.
Oh, sorry.
Yeah. Yeah, so general thing most people start off with is putting some smaller values like one or as you said zero, but you can't obviously put zero here. But putting one doesn't here give anything significant if you can see. So, but you can I think bound something with putting m is equal to one, but that doesn't help like directly.
But
Also,
putting
I okay, but also we'll use this notation for the thing like throughout this lecture. So just tell me in this format. Yes, what were you saying?
I was telling that if we put m equals to n, then we might get some bound.
Okay, okay, I'll just put m is equal to n. So p of n comma n, which gives n square plus f of n divides n f of n plus n. Yeah. How do you bound this? Wait. Okay, so you're saying you multiply this by n times and subtract it.
No, actually, I think that n square plus f of n must be less than or equal to n f of
Yeah.
n plus n.
Okay. Oh yeah, you get some kind of bound, I think. Actually, this is yeah, but this is obviously positive. So you get n square minus n, which is then equal to n minus 1 f of n. Okay, you get this, which means f of n is greater than equal to n. Yes, so you have this. Did everyone get this? What I did here?
Yep.
In fact, you could have an upper bound as well from, but you need to figure out f of 1 for that. So what I was saying was if you have this, so you'll have 1 plus f of n divides f of 1 plus n. F of n is less than equal to n plus f of 1 minus 1. But you don't know what f of 1 is right now, so you can't really conclude much with this.
Can you define your new notation?
Wow.
Can you define your new notation?
Oh, okay. Wait, this notation. Okay, yeah. So basically, p of m comma n is this assertion, right? So if I write p of m comma n, then I'm putting m here and n here. So basically, in this, like I wrote p of 1 comma n, so that means I'm putting 1 instead of m. Do you get this? Like this is a standard notation we use in FE.
Yeah, okay, okay.
This is just to make things simpler. I don't want to write m is equal to 1 everywhere. So you do have this bound, like you do have an upper bound as well on f of n, but you don't really know what f of 1 is right now. So it won't really help that much. Also, apart from just bounding, you need to, use the divisibility in some sense. Like you need to like currently you're only using divisibility just to obtain bounds, but it is a much stronger condition. So Okay, most till now we have almost tried all the, obvious assertions you could have, like one and n. Now, but you see, like nothing is really giving us anything significant. Yes, what?
I have got f of 1 divides 1.
How?
If you put m equals to f of 1 and n equals to 1.
Okay. N is equal to f of, okay, so you're saying this.
No, m equals to f of 1.
Oh, okay, so the reverse. This.
Yes.
Okay,
So we
what
get
does this give?
f of 1 square plus f of 1 divides f of 1 times f of 1
Yes.
plus 1.
Okay.
Now f of 1 obviously divides the left hand side. Hence it also divides the right hand side.
Okay, so f of 1 is 1. Yes. Okay,
Yes.
this is a much cleaner finish. Let me check this. This I think works now. So you have f of n less than equal to n. So you have f of n must equal n.
Here I have a little doubt.
Yeah.
Doesn't we do bijectivity, something like that stuff for this to be
What for what?
for putting m is equals to f1?
No, actually, wait. For no. F of 1 is actually an integer, so you can put like it's in the domain. F of 1 is by definition in z greater than 0, right? So you can put it like as a number.
Oh, okay.
We are not saying that. So for okay, so if you were suppose saying like there is a c such like there is a c such that f of c is something, and you are like fixing this something, then you need surjectivity. But here we are like using it as a number, and obviously it's in the domain, so you can put this. This is fine. Okay,
Okay.
this works. I think this is a much nicer solution. Okay, but what I had in mind was I also discussed that. So basically, let's try to work with prime numbers. Okay. So what happens if you try to use primes in this? What's the first basic thing like? uh, so basically, what I'm trying to say is that can you figure out what f of prime must be? Okay, this is a correct solution, but like if you try to think about this. So the thing is that if you see here, basically this is m square plus f of n divides mf of m plus n, right? So you like even what he did here was that he tried to make everything in terms of f of 1 on this side, right? So that he could, take f of 1 common from here. So we'll try to do something similar here as well. Let's, try to make m also equal to f of n. So what happens if you put that? Basically this. So this gives
F of n divides n.
divides p. Yes. Like if for a prime p.
Yeah.
Yes. So what was left as plus p. So this implies f of p divides p. And but from here you cannot say that f of p must be p. It could be 1 or p. Right.
Yep.
Yes. So now basically you're uh, in a position like you have something, but it's not really concrete. Like it could be 1 or p. So what generally you try to do is try to assume that it is 1 for some primes and then try to arrive at a contradiction. So how can you proceed with this?
For like p square divides 2p.
Okay, how?
Like if we
What?
put f of p is equals to 1, then p square must divide
Where in what equation? Like in the first equation, what are you like putting there? Can you?
p comma p.
Okay, p comma p. Fine. So p comma p gives p square plus f of p. P square plus 1 divides p plus p. Yes. P square plus 1 divides 2p. Yes. Okay.
Now we
So
can know that
yeah,
p
and
square.
this also forces p is 1. Yeah, which is not possible. So yes, like basically this is a contradiction. So yeah, so okay, so did everyone get these two solutions? This was a much cleaner finish, so I didn't think of this. But in general, ideas like this also help. Like if you try to basically reduce it to something dividing a prime, then you can get a lot of stuff, and then you could try to arrive at a contradiction. Does anyone have any doubts on this?
No, no doubts. Just I learned that that trick is helpful. The previous one trick, putting f of m, we could just reduce it and take out a factor.
Yeah. Okay, yeah. So sometimes putting like a value of the function also helps. Like here you could basically bring everything in terms of f of 1 and then you took f of 1 common. So yeah, that helped here. So these kind of assertions are also, very common in FEs. Okay. So I think no one has a doubt. So let's do, which one should we do? Okay, let's do this one. This is also very similar in spirit to the previous one.
Again, possible solutions, f of a is equals to, f of x is equals to x is a possible solution.
Yes.
I got like f of 1 equals to 1.
Okay, how?
I put a equals to b and a equals to b equals to 1. So I got f of 1 plus 1 divides 1 plus f1 whole square.
Yes.
From that, I subtracted f of 1 plus 1. So I got, after factorizing, f of 1 times f of 1 minus 1.
Yes.
So f of 1 plus 1 and f of 1 are co-prime since they are integers. So f
Okay.
of plus 1 divides f of 1 minus 1. And through bounding, I got that the right hand side must be 0. So f of 1 is 1.
Okay. Did everyone get this?
Yeah.
This is one thing we got. F of 1 is 1. Yes.
So if we put a is equals to 1 and so we'll b is equals to b, we'll get that b is smaller than equal to f of b.
1 plus b divides 1 plus f of b, right? You'll get this. Right. Yes. So what were you saying from here?
b is smaller than equal to f of b.
Yes.
Brother, I continued with.
What?
Am I audible?
Yeah.
I continued with if means a equals to 1 and b equals
Yes.
to p minus 1.
B equals to p minus 1.
Yes, where p
Okay.
is the prime.
Yes. Okay. So you get p divides 1 plus f of p minus 1, right?
Yes, and then again by bounding we get 1 plus f of p minus 1 is less than equal to p. So it
Yes.
and since it is also positive, it could only be that f of p minus 1 equals to p minus 1.
Wait, how? What? This is fine, then what?
Oh, sorry,
We'll get this bound
this
only.
one word, sorry.
You have this bound. You have a lower bound on this. But yeah, he's on the right path. Like you should try to work with primes.
We have that f of 2 is equal to 2.
Okay, how? Hmm.
You have to put a is equal to any integer and b is equal to 1, then you get the result.
Wait, how do you get f of 2 is equal to 2 from here?
Yeah, by putting b is equal to 1, we have that
You have this. Okay, so I think I get what you're saying. So you'll do f of a plus 1 divides a square minus 1, and then you'll say, let's put a equal to 2 there. I think this is what you mean, right? So you get f of 2 plus 1 divides 3. F of 2 plus 1 is equal to 1 or 3, but obviously it can't be 1 because it has to be a positive integer. So f of 2 plus f of 2 must be 2. Did everyone get this?
How the RHS is 3?
Oh, I put a equal to 2. Basically, this is p of 2 comma 1. After this, like after I first subtracted f of a plus 1 from this. So I have f of a plus 1 divides a square minus 1.
Oh, okay, okay.
Then I'm putting a equal to 2 here. So everyone got this. But yeah, this is like you're trying to work for smaller values. In fact, if you could have like found a way to make this prime, then you would have, figured out many values, but there is really no way to enforce this as a prime.
Am I audible now?
Yeah, you are audible.
Yeah, I have an idea. If a square minus 1 is a prime,
Yeah,
then we
okay.
have that f of a equal to a.
Yeah, okay. I was talking about that. If you had that, then it would have been much easier. But a square minus 1 being a prime is like it's not very easy to find such a's for which this is a prime. Like in this case, 2 was there, but in general, you will not be able to find a's for this. Okay, but yeah, like you are trying to
Can
make
we
stuff a
prove
prime,
the
right?
function is non-decreasing? Can you prove the function is non-decreasing?
Non-decreasing. I don't know of a way to prove that, but if you do have a way, then tell. Okay, you haven't tried really k comma I till now. That also gives something. Okay.
I did the same thing with primes, but I'm not
Yeah,
able to.
okay. Okay, you did p of p comma p. Does give stuff. So you have this. Now, you obviously don't want to have f of p here as well, right? So what is this like if you basically see f of p is congruent to minus p mod f of p plus p, right?
Yeah.
So f of p plus
I think
p must divide uh, minus p square plus p square also.
I think we can solve it using induction.
How do you induct?
For f of 1 equals to 1,
Yeah, you have the base cases. Yes. F of 1 equal to 1 and
and
f of 2 equal to 2 you have.
yeah, and we can put m equals to x plus 1 and n equals to x.
M is equal to x plus 1 and n equal to x. Okay. So what do you get? Uh, x plus 1 squared plus f of x plus 1 times f of x. Uh, wait, and this is divisible by, so wait, I'll write it here. P of x plus 1 comma x. So you have this. This is divisible by f of x plus 1. I think you wanted to say the reverse, or did you want to say this only?
Yeah, this one. And
Okay,
then we can subtract the LHS x times.
okay. X times. Okay, but okay, you are assuming f of x is x, so I'll just write it here. Induction. X plus 1 squared minus x. Okay, yeah. And after this,
Then I think we are done by bounds.
how, okay, you get f of x plus 1. Okay, yeah, right. And you had this is greater than equal to x plus 1. Yeah, this was nice. Did everyone get this? What you did here? So basically, he has the base cases f of 1 is equal to 1 and f of 2 equal to 2. So now he is basically using induction and he's assuming f of x is equal to x till some x, right? So now if you put x plus 1 and x, you get this. And because f of x is equal to x, I've written x here directly. And now he's subtracting x times this from this side, and you get this is divides to x plus 1. So you have f of x plus 1 less than equal to x plus 1. And from this argument, you had f of x plus 1 greater than equal to x plus 1. So you have f of x plus 1 is x plus 1. Did everyone get this? What you did
Uh,
here?
how is the third line? How did you reach the third line?
From here. Oh, this is my bad. Wait. I wrote it wrongly. It's x square. My bad. I subtracted x times this from this side.
X times. Yeah, yeah.
Yeah, I wrote. Okay, so this is clear, right? This thing. This is also a correct solution. Yes, this is correct. But I'll continue with this approach as well. Did everyone get this? I think nobody has an issue there.
Yeah, this is clear.
Okay. So now we'll proceed with your idea to put p comma p here. So you get f of p plus p divides 2p square, right? Did you understand how I got till here?
No, I actually lost between when you took
Yeah, okay. So this thing was congruent to minus p mod f of p plus p, right? So I'm basically using the Euclidean GCD thing and I'm reducing it to p square. So basically f of p minus p square. Okay, right. Did you get this like from here? How I use these two to get till here?
No, this is I'm confused in the loop.
Okay. Yeah. So suppose how do I explain this? Yes. Okay, so suppose there is something d divides a d plus b. Like okay, yeah, square. So what does this imply? Basically, if you see, so yes, so d divides a square d square plus b square plus 2ad, right? And both of these terms are divisible by d. So d must divide b square. That's what is happening here. So basically, the remainder that this thing leaves when divided by 4p plus p is minus p, right? This is actually the remainder here. If you divide this thing by d, then you have b as the remainder. So I'm just putting the remainder square.
It's hard to follow what you are saying this thing because I cannot see your cursor actually.
Oh, okay. Okay, fine. So basically what I'm saying is that, okay, so d divides, suppose you like look at this first, like d divides ad plus b squared. Okay, and b is the remainder when you divide this whole thing by d, right? Because this is like a is some constant, b is some constant. This is not related to the problem. I'm just, wait, which line are you talking about? I don't get you. Where? This? Okay, wait, I'll explain this again. Never mind. I'll just explain it at the bottom. So, okay, f of p plus p divides f of p square plus p square, right? Okay, so this was the thing we had. This is fine, right?
Yeah.
Now, okay, so now suppose d divides a square and a was congruent to x mod d. Suppose you have this. Then what I'm saying is d divides x square. How? So basically, suppose a is equal to d times some z plus x. Then d divides dz plus x squared. D divides d square z square plus x square plus 2x dz. This implies because these two terms are divisible by d, so d must divide x square. Is this fine? What I
Yeah,
did
yeah,
here?
yeah. This is clear.
That's exactly what I'm doing here. So I'm basically just substituting f of p by minus p because f of p is congruent to minus p mod f of p plus p. So I'm just
Okay, got it. Now got it.
yeah, okay. So this is we have this. Now do you get like whoever was writing in the chat? This is fine, I think. Okay. So f of p plus p divides 2p square. And now you have like only a certain specific values of p which can work. What are those? Like this has very few divisors. Assume p is greater than 2.
P.
Yes. What else? I think 2p square minus p also. And what would be the factors? I think 2p.
P minus 1.
Yeah. No, wait. How p
Oh, no, no,
minus
no.
1?
Okay, it's P. It's P.
2p. I think 2p square is a divisor. Use that. 2 minus p it couldn't be because I'm assuming p greater than 2. Then there is a divisor p. Can't be because this is all obviously greater than p. P square. Okay, yeah, p square minus p. I think only these three work. No others. Is this fine?
Yeah, p square minus
Yeah.
b. Yeah.
Okay. Yeah. So you have these three. Now, wait. Now what? Now how can you? You basically want to eliminate these two. So how can you eliminate these?
Maybe some contradiction if we use
Yeah. How do you achieve a contradiction? You also have f of 1 is equal to 1. So maybe try using that as well. Also, I think you had some stuff as well before. Let me check. Oh yeah, you have this as well. You have f of a plus 1 divides a square minus 1 for all a. I think this should be enough to eliminate these. Like if you put a equal to p here, you get f of p plus 1 divides p square minus 1. And it can't be both of these, I think. If you have it as 2p square minus p plus 1 divides p square minus 1, then by bounding you have 2p square minus p plus 1 must be less than equal to p square minus 1, which means p square minus p must be less than equal to plus 2 must be less than equal to. I think this is false.
Yeah.
For larger p, this is false, like for p greater than 2. And even this you could eliminate. So p square minus p plus 1 must divide p square minus 1. If you subtract it from here, you have p square minus p plus 1 must divide what? P minus 2, I think. And even this is false. Like for p greater than 2, this has to be obviously bigger. So, so both of these are like eliminated.
Yeah.
Okay, so you have f of p is p for all primes p. Now, how do you use this to get f of n is equal to n for all n?
I guess f of a into f of b gives a hint. We can write some number as a product of primes. P comma let's say p comma q, that might work.
Wait, what are you trying to set in it? What are you like? You are trying to make this as a product of two numbers or what?
Yeah, p comma q.
Basically, now you have f of p is p, so you should be like trying to have one of the numbers as a prime, and that would be preferably a, because you had like because a is mostly occurring inside the function, so you try to want to have a as a prime so that you already have this as p. Do you get what I'm saying? Like basically you want to use this now in this FE.
Um, from putting let's say f of sorry p comma let's say p comma b,
Yes.
we get p plus b divides p into p plus b.
Yeah, but this is 2. So this doesn't give anything.
Sorry, p square plus pfb.
Oh, this is my bad. My bad. Yes. Okay, so you
That's
get p plus b divides, I think, f of b times, uh, if you
p
subtract
times.
it, pf of b minus pb, right? You get this. P plus b divides p times f of b minus b. You get this, right? It's this fine.
Yeah,
Actually, from here now you are done. So again,
we can.
p is congruent to minus b mod p plus b, right? So again, you could basically just substitute this here. Do you get this?
Yeah.
And now the idea comes into your hand that you can make this like large enough. You can make p very large, and this would and keep b fixed. So at some point, this would obviously be bigger than this in absolute value. So this has to be 0. Do you get this? Like if you make p much larger than all of f
Yeah.
of b and b.
So now we know that b cannot be 0, so f of b minus b.
So f of b must be 0. Oh, f of b must be b. Yeah. So this was the proof. Did everyone get this? Like what we did here? Basically, this idea came into play that you can make the left hand side very large, and because it is dividing something, so the other thing must be 0.
Yeah, also this mod p plus b, using that is also very useful.
Yeah. So in general, like whenever you have such divisibility stuff, you could just basically replace the thing with the residue modulo that number. Even in squares, all of that, like even in basically I proved it for a square here. You can even do this here. You can expand with binomial and all, and you'll have this as well.
Yep, only the last term, one term will be of x,
Yeah,
which.
yes. Which, so I think nobody has a doubt in this. But yeah, this induction also works here, which you told. Induction also is a solution here. So I think we can do now. Let's do. Wait. Let's try something different. Let's do this. This is actually not uh, NTFE as such, but I like this. So
Here a is just a power, na? Like f of
oh,
b.
okay, yeah. So fk of n means f of like k times.
Oh no, that is.
It's written here.
So what will be actually if we put like f of, like k is equals to 0, so f of n, what will be that?
Oh, so if you put k is equal to 0, then it would be n. F0
Okay,
of n is n. So let's try, the okay,
f
what?
of a comma 0, then we
Yeah,
get
okay.
1
I think you get this.
of 0. Yeah, f of 0 is equal to 2a.
F8 0 is no.
Yeah, f of a.
What can you conclude from this? You can conclude something more from this.
Subjectivity.
F of 0 is equal
Okay, you have subjectivity, yes, but not subjectivity exactly because you only have even values till now.
Oh
f
yeah.
of 0 is equals to 2.
Yeah, you have f of 0 is 2, but you have something more.
Uh, we know all the values for even n.
Yes, how?
That f of a0 equals to 2a plus
Yeah,
1, and that is
okay,
f of
yeah,
2a.
I get it, yes. So basically, what he's doing is he's taking the f on both sides. So you get this, right? And this is f of a plus 1, 0, which is 2 times a plus 1. So you have f of 2a is equal to 2 times a plus 1 for all a.
Oh yeah.
This is actually, an important technique in functional equations that if you have x is equal to y, then, taking the f on both sides also helps a lot of times. So you have already determined that f of n is n plus 2 for all n even. Now you need to also, yeah. So if you check, I think, yeah, f of n is equal to x is equal to x plus 2 is a possible solution for all x. Although you'll not be able to spot it very quickly, but yeah. Now you can see, like after this, you can spot the solution. So you have to try to prove, like find f of n for odd n now and try to show it's equal to n plus 2. Also, because you have like f of n is n plus 2 for n even, you need to use the like try to make one of a and b even so that you have some
Yeah,
stuff.
I was doing the same, b even and a letting odd, so maybe we could get some.
Okay, so you want to make b even and a odd. Yes. So let's try that. What do you have? Okay, 2k plus 1, 2k, 2k plus 1, 2k minus 2k, 2k plus 1 is equal to 1. Okay, wait, let's just make it general. 12, so you have 2l plus 1 minus 2k. And this is 2k plus 2 times 2l plus 1 minus f2k of 2l plus 1, 2l plus 1 minus 2k, and this gives f2k of 2l plus 1 equals 2k plus 4l plus 2 minus 2l plus 1 minus 2k, which gives 2l plus 1 plus 4k. Did everyone get this algebra I did here? I basically just used like the thing for even here and got this.
What is L here? I couldn't get it.
Oh, okay, so L is any natural number. L and K are both just and z greater than or equal to 0. You wanted me to put A as odd and B as even, right? So I just wrote it them like 2k plus 1 and 12.
Okay.
So this is clear, right? So you have something for odd, but there are like two variables and it's hard to control. So maybe try to put some specific values for k. Also, instead of this, you could probably have this as well. Like instead of putting 2k plus 1 here, even if you would have put 2k, it would have still been the same. Like you never used this being odd, right? So you in general have this. I could write it here. So this you get from using I think yeah, you use. Wait, did I mess the notation up? Okay, my bad. I think this one messed it up. Well, that's why I did that. So you could just put n comma tk here, and you will get this. Do you get how would you get this? Like you can try to work this out. The same calculations, you will get this. Is this fine? If you have a doubt, I can work this out.
Can you please show from
Yeah,
line?
okay. Okay, I'll just show this. Yes. So I'm basically putting A as n and B as 2k. So you have f of so you have f of n 2k minus f of 2k n is equal to n minus 2k. Right? N could be anything here. Now this is 2k plus 2n, right, from our claim for even n.
Yeah.
And minus f2k of n is equal to n minus 2k. Just bring it to the other side. F2k of n equals n plus 4k. Is this fine now?
Yeah. Yeah.
Okay, so you have this. So you have some, like if you have n odd, so you have something for n odd. But this k is, maybe you can try putting some specific values of k and obtaining something.
Okay. If we put k is equals to 2 and k is equals to 4,
Yes.
then for k is equals to 4, we can substitute the value what we got k is equals to 2, and that gives f of n plus 4 is equals to n
Do you mean
plus,
k is equal to 1? I think you mean that.
yeah, k is equals to 1 and k is equals to 2.
Yeah. Okay. So you get f of n is n plus 4 from this. And after using k equal to 2, you're saying you get f of n is equal to n plus 8, which is equal to f of n plus 4, right?
Yeah.
But you will get the same thing from these two. You'll get this only. So k equal to 2 doesn't really help that much. But yeah, you get this f of n is n plus 4.
Okay. Yeah. I found it. Okay.
You'll get the same thing. Like if you substitute that thing as well, you'll get the k equal to 1 condition only.
Yeah.
But you do have this. Now you need to just reduce it to f of n is n plus 2. Again, what I said, like if you have x is equal to y, a general idea is to take f on both sides. Especially in involution. So do you guys know what an involution is? This is
Yeah.
similar to what an involution is, right?
Yeah.
Like if
I
so
I
the
read
triple
that.
F trick. Yeah, the
Yeah.
triple,
Triple F.
it's called the
That's
triple. So we are going to use that only. So taking the f on both sides, you have this. So you have some sort of linearity as well. Okay, I'll add it to the initial thing as well. This is These two are general ideas for FPs.
Now, can we use somehow bounding?
Mm, how exactly? You can try to use some sort of induction from here, I think, but how bounding? Like you can do you like see why I'm trying to say induction? Because if you can figure out f of 1, f of 2, f of 3, all of f of 2 you already have figured it out. But if you can figure out f of 3 and f of 0, I think yeah. Yes. Wait, where is the problem? Yeah, okay. So if you can figure out these three values, then you can just induct and you can like get f of n is n plus 2. Because using this, you can just make jumps of 4. And out of these two, you already have these two values. But sometimes it's the case that even finding these two is quite hard, which might be the case here.
Actually, after this involution, I read the same thing. Just 4 was replaced by 2 there.
Yeah, but like here you get it as 4. So here you get a jump of 4. In some different problem, maybe it was n plus 2 here or something. You can get a jump of 2 as well. So basically here, if you were trying to find f of 1, you must have faced some difficulty. In general, like in good FEs, even like finding f of 0 and f of 1 is a problem. So mostly what you do is like you assume it to be some number and then try to work with this number. here basically you do realize, right, ki if you just like find f of 1 and f of 3, then you are done. Because then you can make jumps of 4 and basically cover everything. So maybe try to work with what f of 1 and try to find, like, just assume f of 1 is something and then put it in the equation and try to find something.
Can I
Yeah, go on.
just opened when I saw the problem, like that f of plus x plus 2 1. So there it was written that f of x is smaller than f of x plus 1 is smaller than f of x plus 2. So f of x plus 1 must be equal to f of x plus 1.
Wait, but here you don't have any decreasing or increasing condition, right? So you can't really use any of that. Here you just have that f of n plus 4 is f of n plus 4.
Oh yeah, okay.
Okay, what happens if you put 1 comma here? Right?
Yeah.
And wait, not this, f of k. And so you have f of k plus k minus 1 is fk of 1. Again, try to use the thing I told, like take the f on both sides. But now you realize that taking the f one time won't help, right? Because you have f of something and you can't really make sense of this. But if you take the f 2 times, then you have something nice. So what you have is that this is f of k plus 2 of 1. And now you can use this thing. F of n is n plus 4. So you have f of k plus 3 is equal to fk plus 2 of 1. Did you get this, what I did here? Basically, if you would have taken the one time on both sides, then this you can figure out, but this you can figure out by the thing fk of n is n plus 4k. But the thing is that you can't figure out this really for now, because the issue is that uh, f of something, it is f of something and you don't know what the something is. But if you take the f 2 times, then you can cleanly reduce it to this by using this. Did you get this? Or if someone has a doubt, then they can just ask.
Yeah, this is clear.
Yes, and now let's just basically put k plus 2 here. So you get f of k plus 2 plus k plus 2 minus 1 is equal to f of k plus 2 of 1, right? This is f of k plus 2 plus k plus 1, and this is equal to f of k plus 3. Basically substituting it here, which gives you f of k plus 2 is f of k plus 2 for all k.
Can you
Is this
please
fine?
repeat this
Oh,
this last
okay.
bit?
Yeah. So basically, what I did was I put f k plus 2 here instead of k. So you get this, right? If you put k plus 2 everywhere instead of k.
Yeah.
And now what I got here, the value for f k plus 2 times of 1, I substituted it back in this equation. This equation. Like this value I substituted here and just equated these two. So you get f of k plus 2 is f of k plus 2. Is this fine? I assume this is fine then.
Yeah,
Because-
clear, clear.
Okay, yeah, okay. So this is fine. Okay. So now instead of a jump of 4, you now have a jump of 2. So you only need to figure out what f of 1 is now. You have f of x plus 2 is f of x plus 2 for all x. So basically, yeah, you have this.
First time where the f of one thing is last thing we have to prove.
Yeah. Now you only need to prove f of 1 is 3. Because after that you have f of 0 is 2 and f of 1 is 3. And then by using induction and this condition, you can have f of n is n plus 2 for all n. In fact, if you like, suppose f of 1 is c, then you have f of n is, uh, sorry, yeah, f of n is n plus 2. Wait, what is it? Let's just work it out. Okay, so f of 2k plus 1 equals 2k, 4k plus, no, wait, f of n is n plus f of 1. You get this. Like if you just induct, so basically what I did here for all n, for all n odd. So basically what I did here was that f of 2k plus 1 is f of 2k minus 1 plus 2, which is f of 2k minus 3 plus 4, and so on, right? So eventually you will reach f of 1 plus something. If you calculate that, I think it comes out as this n minus 1, which is in this case 2k. Did you get this? Like I built a chain basically.
Okay, so mine from where minus one came.
Oh, okay. So that is just okay. So let me write it like this. F of 2k plus 1 is f of 2k minus 1 plus 2, right? Which is f
Yeah.
of 2k minus 3 plus 4. And if you like keep on doing this, then you'll get f of 2k minus 2k minus 1 plus how much? 2k. Do you see, like you're subtracting an odd number and then you're adding 1 plus that odd number?
Yeah.
The pattern
Okay.
is like that. And so this is f of 1 plus 2k. And if I just say n is equal to 2k plus 1, then I get this. So you have this for n odd. Now you need to just figure out what f of 1 is and then you are done.
plugging n is equals to 3 works.
Where?
What we have found, f of n is equals to n plus f of 1 minus 1.
Yes, but what does it give if you put n equal to 3? You don't have f of 3 as well now, right now.
Oh, we have it in the form of f only.
Yeah, you have everything in the form of f of 1, like f of all odd n. So you need to find f of 1. So in general, like whenever you're a good idea always is to once like substitute the thing you get in the original functional equation. So you do have f of n is n plus f of 1 minus 1, right? But let's try to substitute it in the original equation with one thing odd and one thing even, as we were doing. So let's put a as odd and b as even. Is equal to a minus b. Let's say a is odd and b is even. So because a is odd, so b is even, so this is b plus 2a, right? This we know from this claim. Yeah.
Yep.
And this thing is basically a plus, if you like keep doing on this, then it would be a plus, what would it be? A plus, how many times this? I think b minus 1 times f of 1 minus 1. B times f of 1 minus 1. I think, yeah. If you keep on like taking the f on both sides, and like if you
The
needed
same
this,
thing we did just now.
yeah, like you can say from this. Uh, wait. Yeah, okay, yeah, just keep on using this. F of 1 is n plus 4, and you'll get this, I think. Let's try to, wait, I'll do the calculation. I think you get 2b minus a minus b, so you get f of b is what? Uh, wait, it is b plus 2. So you get f of b is how much? 2b plus a, yes. F of b is 2b plus a, right? Now you have f of a is a plus f of 1 minus 1. Yeah, and now just put b equal to 1 here in this equation. So you get, wait, but you can't put b equal to 1, never mind. Mhm.
From here, can't we get f of 1 is equals to 2b plus 1?
Wait, how do?
Oh, it's f of b times f. Okay, here we just have one time.
Yeah, yeah, yeah. Mhm.
Putting b is equals to 1.
You can't do that actually because b we have used it as even. Yes. We go to think first. We have this, and what else did we have? We had this is a plus f of 1 minus 1. What did we put fb of 1? gives us 2b plus 1 and this one.
Yeah, I guess if we put b is equals to 2, then we can substitute f of a plus f of 1 minus 1.
Okay, so what are you saying? F of a is equal to a plus 4. Then what you're saying?
F of a substitute
A
equal
plus
to.
f of 1 minus 1. Okay. This gives you this is a plus 4, but then how do you conclude from this?
Now again, we can't do the same thing like we did for f of a. We can now do it for
Okay,
f of.
yeah, got it. Yes. So, okay, so the thing is that now if you take f on both sides, yes, nice, this works. This is equal to f of a plus 4, right? If you take the f on both sides. And this is equal to a plus f of 1 minus 1 plus 4. And this is equal to f of a plus 4. Wait, no. Uh,
No, just like we have got something f of n is equals to some a plus 4. So
yeah.
like again doing that, we get a plus f of 1 minus 1 plus f of 1 minus 1 is equals to a plus 4.
What? Okay, oh. But you don't know this is odd or even, right? You don't know yet if this is odd or if this is even.
Okay.
But I think you can just make cases. Okay, so suppose if a plus f of 1 minus 1 was odd.
No, but a is fixed, na, a is odd.
Yeah, no. But the if suppose this thing was odd, I'm saying that. Like if this whole thing was odd.
Okay.
So you get the a plus 2 times f of 1 minus 1 is a plus 4, which gives you f of 1 is 2. Which gives you f of 1 is 3. So this case gives you f of 1 is 3, and if you assume the other case, you'll have a plus f of 1 plus 1 is equal to a plus 4, which also gives you f of 1 is 3 if a is even. Okay, did you get this? So what I'm saying is that if, wait, not this, if a plus f of 1 minus 1 is even. Yes. So basically, I'm making two cases. So if this was odd, then this thing was equal to this thing plus f of 1 minus 1, as you said, right?
Yeah, yeah, got it.
In that case, it's f. In that case, you get f of 1 is 3, and even if you assume it is even, then you already have this is f of n is n plus 2 for even n. So
Yeah,
in that
plus.
case as well, you get f of 1 is 3. So in both cases, you get f of 1 is 3, and you're done. Yes, nice. This is good. Fine. Does everyone get this? I hope. Although this was a bit tricky. This problem was tricky. I planned on doing a few more problems, but I think I'll just add them in the P set. So does anyone have any doubts related to the class? Any problem you can ask.
Can you show the last step again?
Oh, this step. Okay. So we had this, right? Did you get this? Like how we arrived at this? We took the F on both sides.
Yeah.
Okay, so now we are making two cases. Suppose a plus f of 1 minus 1 was even, or a plus f of 1 minus 1 is odd. If it was even, then we already know that f of n is n plus 2 for all even n. So this would be equal to a plus f of 1 plus 1 is equal to a plus 4, which would imply f of 1 is 3. And if this was odd, then we know that f of like n is equal to n plus f of 1 minus 1 for odd n. So because this is odd, so this is equal to a plus f of 1 minus 1 plus f of 1 minus 1. And this is equal to a plus 4. And if you solve this, you get f of 1 is 3 from here as well. So you get f of 1 is 3 in both cases.
Yeah, got it.
Does anyone have any doubts related to this problem or the previous problems? They can ask. Also, I'll just add that idea here.
We learned many things from these questions today.
Yeah. In FEs, mostly you learn stuff on the way. As you do more problems, you try to see like what substitutions you can make, and even the triple F trick
Yeah,
and all.
this problem is amazing.
Yeah, this is actually not NTFE, but I like this a lot, so that's why I kept it there. Apart from this, maybe you can try this. I'll not put this in the PC, but I'll just put it here. This is also very weird problem, but I don't think we have the time now to do this. You guys can try this later.
Here there are two functions, right?
Yeah. So yeah, you guys can try this later. Does anyone have any doubts? Otherwise, we can end the class here, I think.
Really enjoyed the class though, no doubts.
I should make a poll, I think. How do you make so I think if nobody has a doubt, we can end recording. I think we can end the class here then, if nobody has a doubt. So thank you everyone.